We begin today's session by reviewing what we have covered in terms of the concepts in sampling that we have done yesterday, and to build on that and to touch upon the aspect of reconstruction. Reconstruction is the process by which we go from the discrete time back to the continuous time. So, this is what we call as reconstruction. So, we will touch upon both these concepts today and build on that by using some examples. So, let us quickly review what we have covered yesterday and to make sure that we are comfortable with the mathematical framework which we have derived in the last lecture. So, the Nyquist Sampling Theorem, I am now fairly confident that you are very comfortable with the concept of Nyquist Sampling Theorem. You always want to find out what is the highest frequency component that is present in your signal. The signal will have some highest frequency component because it is a band limited signal, the frequencies will not go to infinity. So, you find the highest frequency component and then pick your Nyquist sampling rate to be twice the highest sampling frequency, highest frequency content. Now, you can go higher than 2 times, that we saw that there is no harm. So, for example, we saw in this figure on the right hand side, you have samples which are at a certain spacing, and on the left hand side you have samples that are at half the spacing. Now, if both are able to reconstruct the signal, if both have satisfied the Nyquist criterion. So, over satisfying the Nyquist criterion is not a problem, it is actually a good thing because it will help you to reconstruct the signal, as we will see in today's lecture. Doing higher than the minimum sampling rate required, higher than the Nyquist rate is actually quite advantageous for us. So, we looked at several examples. We looked at the frequency content of the signals by looking at the Fourier transform. So, that is an important element that I would like you to keep in mind. So, in order to apply the Nyquist sampling rate, so basically we want to look at what is the Nyquist sampling rate. With sinusoids is very easy, but if you have any other signal, then it is good to go to the Fourier transform domain. Okay, look at the Fourier transform of the signal, and that will tell you what the frequency content is present. So, for example, if you have a continuous time signal xc of t, look at the Fourier transform xc of j omega. Now, xc of j omega will be band limited. So, you will look at the frequency response and look at what is the, so minus omega n to omega n. So, the band limited frequency is omega n. So, this knowledge this ability to understand what is the highest frequency component comes from looking at the Fourier transform. That's an important aspect. In fact, we did an example yesterday. I will just repeat that, just mention that for your reference. So, we had a signal xc of t given by sinc of 200t. Okay, we said that the definition of this signal is sine 200 pi t divided by 200 pi t. Okay, this was the time domain signal. Now, rather than guessing what is the highest frequency component, we said that we would look at the Fourier transform of this signal. The Fourier transform of this signal looks like this. It is a rectangular function with a height of 1 by 200, and what is important, what is of interest to us is what is the highest frequency component. It is from minus 200 pi to 200 pi. Okay, so then once you know that the highest frequency component is 200 pi, then you say that the Nyquist sampling frequency must be equal to 400 pi, and correspondingly what the frequency content are. Okay, so I hope you are comfortable in applying the Nyquist sampling rate. You always would a good idea to go to the Fourier transform domain, look at the spectrum, find out what is the highest frequency component, and then apply twice the highest frequency component, and keep in mind that you can over satisfy the Nyquist criterion. You can sample at a rate higher than what is specified by the Nyquist rate, and it is actually advantageous for us. Now, this slide is extremely important because this gave us the complete mathematical framework for the sampling process. So, we had a continuous time signal that was band limited. So, this is a band limited signal xc of t, for which we have determined what is the sampling period, Nyquist sampling period, that is Ts. So, you have to choose it to satisfy the Nyquist sampling rate, and then visualize the signal s of t, which is a train of Dirac delta functions. We said that because this is a periodic signal, we can also write it in terms of the Fourier series. So, basically equation number 1, which is the Dirac delta, can also be written in terms of the equation number 2, that is the Fourier series representation. So, 1 and 2 are exactly the same signal expressed in different forms. Now, once you have an expression for s of t, we can then obtain the Fourier transform. And when you have exponentials, what you get is 2 delta functions for each exponential and with a scale factor of 2 pi, and that is exactly what we have shown here to be the expression that we have for. Now, this is the expression for s of j omega. Now, what are we doing in the mathematical framework? We are taking xc of t and multiplying it with the train of Dirac deltas. So, the corresponding Fourier transform representation will be a convolution of the Fourier transform of xc of t to the Fourier transform of s of t. So, the xc of j omega, that is known to us, that some spectrum is given, and you have obtained now an expression for s of j omega. We now have to convolve, and we said that whenever you have to convolve, that essentially means that the original spectrum will move to where the delta function is occurring. So, for example, if I have, maybe I will just do a small box over here. Okay, if I have a spectrum which is like this, okay, let us say it is minus omega n to omega n, and I convolve it with a delta function that is occurring at omega naught, okay, convolution. So, the resultant of this convolution is of the form where the spectrum will now be centered around omega naught, and it will look like, so basically if this is omega naught, the spectrum now is shifted. So, this is omega naught, this will be omega naught plus omega n, this will be omega naught minus omega n. So, now you see you have a string of delta functions. If you convolve x of j omega, xc of j omega with these delta functions, you will get many copies, and that is precisely what we have obtained in this case. Okay. And because we have satisfied the Nyquist criterion, the spacing between these copies is given by omega s, and that is more than 2 times the highest frequency component. So, keep this mathematical framework in mind. Then we said that the representation excuse me, you have the spectrum, signal spectrum, the Dirac delta functions, the Fourier transform of that, and when you convolve, you will get all of these copies. Now, look at omega m equal to 0 and m equal to 1, the 2 copies which are centered around the Dirac deltas that occur at omega equal to 0 and omega equal to omega s. Now, you have 2 copies of the signal. The highest frequency component for m equal to 0 is omega n, and for omega s, the lowest frequency component will be omega s minus omega n, just like we did in this particular case on the top right hand side, exactly same thing we are doing here. So, in order for these 2 spectra not to overlap, we said that the condition that must be satisfied is that omega n, which is the highest frequency component of m equal to 0, must be less than or equal to the lowest frequency component of the first copy on the right, that is omega s minus omega n, and when you compare it, then you get what is the Nyquist criterion. In case we did not satisfy Nyquist criterion, then what you will see is that overlap of the spectra. This is called aliasing distortion. It is a nonlinear distortion, and it is something that cannot be removed from the signal. So once you have introduced aliasing distortion by not satisfying Nyquist criterion, then the signal is distorted and is not possible to recover for us using normal processing. So to summarize everything that we have in terms of the sampling that we have discussed so far, the mathematical framework, we start with an impulse train that has got a Fourier transform S of j omega, which is also an impulse train which is centered at omega s. Now what is omega s? If you want to relate the two, this is equal to 2 pi times fs. That is equal to 2 pi divided by Ts. Fs is equal to 1 over Ts. So this is the relationship that we have, and this is the spacing of the Dirac deltas in the Fourier transform domain. Notice that there is a scale factor 2 pi by Ts. All of these are at 2 pi by Ts. All these Dirac deltas are occurring at 2 pi by Ts. Now when you convolve, the resultant scale factor becomes 1 over Ts. So this is the new scale factor, and that is what you see as the new scale factor of 1 over Ts. Now if we assume that we have satisfied Nyquist criterion, so these copies are not overlapping, and we now have corresponding, this corresponds to m equal to 0. The copy corresponding to m equal to 0, this is m equal to 1, m equal to 2, m equal to 3, this is m equal to minus 1, minus 2, and so on. Okay, so these are the copies of the spectrum produced by convolving xc of j omega with the Dirac delta functions which are located at different points. Now this is the sampled spectrum xs of j omega. So xs of j omega is the spectrum or the Fourier transform of the sampled signal. Okay. Under normal processing, what we will do is, after we have obtained from xc of t, we will get xs of t. This is the xc of t multiplied by the Dirac delta. This is still a continuous time signal. So this is a continuous time signal. Okay. This has non-zero values for all t, for all time. Basically it's a continuous function. This is a continuous time signal which is non-zero only at certain locations wherever the delta functions occur. Non-zero only at nts, because that is where the Dirac deltas occur, right? When you multiply the two together, that is where. And from these samples, we will get the discrete time signal x of n. Okay, that is a discrete time signal. Now when you want to go back to the continuous time, then you have to go back in the reverse direction. So from x of n, we will get something which is equivalent to xs of t, and from there we will reconstruct the signal. We will call that as xr of t. This is the reconstructed signal. Now the guarantee of Nyquist sampling theorem is that if you satisfy the Nyquist rate, then you can go from xc of t to x of n, and you can go from x of n back to the original signal which looks. So in other words, if you have satisfied Nyquist theorem, Nyquist condition, then xr of t must be very close to xc of t, exactly equal, almost exactly equal to that. So this is the process of reconstruction. Now that means the spectrum of xr of j omega must be very close to the spectrum of xc of j omega. How do we ensure that? So, if you look at the spectrum of xs of j omega, let us assume that we have from x of n we have been able to generate xs of t. Now, from here I have to go backwards to getting the the spectrum. So, we see that there are copies, the original copy of the signal is present. It has a scale factor of 1 over Ts and it has got many copies. So, the process of reconstruction first and foremost must get rid of the copies. Okay. So, reconstruction, remove the unwanted copies. Remove unwanted copies, and these are copies which correspond to m equal to plus minus 1, plus minus 2 and so on. Okay, so this is in terms of the reconstruction, and the second one you have to apply a scale factor, because the original one had a height of 1, now you have a scale factor of 1 over Ts, so you apply a scale factor of Ts. Okay, so what is the reconstruction process is to pass this signal through a filter whose frequency response will have a gain of Ts, so that you will get the correct scale factor, and it will have a cutoff such that it will remove all of the unwanted copies of the signal. Where should the cutoff be? You can say that it is exactly midway between m equal to 0 and m equal to 1. What is the center frequency of m equal to 0 is 0. What is the center frequency of m equal to 1? Omega s. What will be the midway? So, the midpoint for the reconstruction signal, this will be minus omega s by 2, because that is, and this will be omega s by 2, okay, on the positive side. So, the reconstruction filter has the following characteristic. It is a low pass filter. It allows frequencies around omega equal to 0. It will pass all frequencies from minus omega s by 2 to omega s by 2. And that means it will get rid of all the unwanted images, and it will leave only the m equal to 0 image, and it will apply a scale factor of Ts, so that it will cancel this 1 over Ts scale factor, and what you will get is exactly a replica of the input spectrum. Okay, I hope you are comfortable with the process of sampling. How you get many copies, what is the scale factor, why did the scale factor come out to be 1 over Ts, all of that was explained in the mathematical framework. Now, given that you have xs of j omega, how do we get back the original spectrum? You pass it through a low pass filter with these characteristics, and this is what is the reconstruction process. Now, the first thing that we would like to do is to understand what is the shape and the behavior of this reconstruction filter. So, this reconstruction filter that is going to operate on xs of t. Remember, from x of n we have generated xs of t. From here we have to go all the way to the reconstructed signal. So, this is the reconstructed signal. We are looking at the reconstruction process. Okay. Now, what is the frequency response we have specified? What is the corresponding time domain response? So, what I would like you to do is to write down the Fourier transform of this function. So, HR of t will be equal to 1 over 2 pi integral minus pi by Ts to pi by Ts. Okay. So, make sure that you write down the Fourier transform integral. The amplitude is Ts for all frequencies of in between minus pi by Ts to plus pi over Ts, and you have e power j omega t d omega. Okay, so basically we are looking at the inverse Fourier transform, and you can verify that this comes out to be sin pi t over Ts divided by pi t over Ts. Okay. Not surprising, because this is nothing but this is exactly the sinc function, sinc of T over Ts. Okay, and the corresponding Fourier transform is this rectangular function which goes from minus pi by Ts to pi by Ts. In fact, we did do the derivation of what is the Fourier transform of the sinc function as one of the examples for applying Nyquist criterion. So, I hope you are able to look at that. Now, I would like you to take, so this is the reconstruction filter. So, what is happening in the part of the reconstruction process is that XR of T is obtained by taking the Dirac delta samples XS of T and convolving them with this impulse response. Now, where did I get the fact that it is convolution? Go back and look at it. What did we do here? You took the spectrum of XS of j omega and multiplied it with the spectrum of the reconstruction filter. Because when you multiply, the reconstruction filter has got zeros everywhere other than the passband, and that is why. So, it is multiplication in the frequency domain. Okay, that is the reconstruction process. So, when you look at it in the time domain, this will be the convolution. So, let us write that down. So, this corresponds to, in the frequency domain, XS of j omega multiplied by HR of j omega. Okay. So, this is HR of j omega, which is a rectangular filter with a scale factor of Ts and going from minus pi by Ts to Ts. Okay. So, the reconstruction process, we know what the filter should look like. We have also been able to obtain what its impulse response is. Now, look at a very interesting property of this particular reconstruction filter. This reconstruction filter, this is called the impulse response of the reconstruction filter. Okay, this is called the impulse response of the reconstruction filter. So, now look at the impulse response. The impulse response has got a very interesting property. It has a value 0 at t. You can substitute sine pi times t is equal to Ts. That means, so this is everywhere, just write it as Ts. This is 2Ts, 3Ts, 4Ts and so on, and similarly minus 3Ts, minus 4Ts and so on. So, whenever you substitute the lowercase t equal to Ts, you will find that you will get a multiple of pi. So, sine of a multiple of pi will be equal to 0. So, you have 0 crossings at every multiple of Ts, both positive side and negative side. Okay. And for how long will this go? Basically, it will go all the way to infinity. Basically, you will have lots of ripples. Eventually, the ripples will die down. But this is the behavior of the sinc function. Now, why is this important? Very, very important concept that we are going to be working with. Okay, so look at this equation. This equation says that the reconstructed signal is a convolution of the Dirac delta samples convolved with the impulse response of HR of t, and this is HR of t. So, now let us look at the the reconstruction process. So, we are basically going to go in the from here. These are the Dirac delta samples, Dirac delta functions, Dirac delta functions. The scale factor is dependent on x of n. Supposing this was 0, this would be, the scale factor will be x of 0, okay, the scale factor. Because remember, we are converting from a discrete time. So, the scale factor will come from the discrete time signal. If this is 1, this will come out to be x of 1 and so on. So, basically the scale factors are embedded in the delta function, but at the end of the day what we have is the delta function of different heights depending on the scale factors. Now, when you convolve, let us see if I can draw the Dirac delta sinc function. So, convolution basically will look like this. When I convolve with the Dirac delta at omega m equal to 0, I will get a response that looks like this. Okay, and convolution of the impulse response with the Dirac delta at m equal to 1. Okay, let one more function. It basically, okay. Now notice that where the original delta function was there, the green contributes only 0. It does not contribute any non-zero value. In fact, all the other delta functions, because of the property of the reconstruction filter, that it is going through 0 at Ts, 2Ts and so on, there is no contribution where the delta functions are occurring. But everywhere else, all the delta functions will contribute. So, for example, what is the value at this point? It is the red plus green. You have to take the combination of these two, and that gives you the value that is. So, you originally had the Dirac deltas at 0, Ts, 2Ts and so on. Now, after the reconstruction process, which is a convolution with the reconstruction filter, then what you have is the reconstructed signal, which will look very close to what was the continuous time signal. Okay. So, what are the important things to remember here? One is that the reconstruction filter has got 0 crossings. Those are very important, because if they did not have 0 crossings at Ts and 2Ts, then the height of the Dirac delta would have gotten modified, because there will be some contributions from the Dirac deltas on both sides. Now, what we find is exactly whatever was the height of the Dirac delta, that remains. Between Dirac deltas, you fill in the value of the function at all values of t. So, basically you go from a function which is only defined at multiples of Ts to a continuous time signal which is defined for all t. Okay. So, this is the process of reconstruction. So, from here to here, this is the process of reconstruction. Okay. So, we can summarize it in the following manner. We can say that we are taking the Dirac delta signals xs of t, and we are going to pass it through an LTI system. So, this is an LTI system which is used for reconstruction. And because it is an LTI system, it will have an impulse response. Impulse response is given by HR of t, and this impulse response is a sinc function, as what we have seen in the previous slide. So, HR of t is a sinc function given by sin pi t over Ts divided by pi t over Ts. This is equal to sinc of t by Ts. Okay, that is the impulse response, and the output will be XR of t, which is a convolution of XS of t convolved with HR of t. Okay. We have looked at it in the frequency domain. What is doing in the frequency domain? The frequency domain, it is cutting off all the unwanted copies and giving the appropriate scale factor. What is it in the time domain? It takes the Dirac delta functions and then fills in non-zero values everywhere between the Dirac deltas. It does not modify the height of the Dirac deltas. It fills in everything in between. So, that is what the reconstruction process is doing. Okay. So, I hope you are comfortable with the expressions that we have written down. Now, if you want to write it down mathematically, then we can look at it in the following manner. XS of t basically takes the discrete time values and scales the Dirac delta function. So, XS of t is a sum of Dirac deltas n equal to minus infinity to infinity delta of t minus NTS, that is just a Dirac delta, and it is scaled by the corresponding discrete time signal which is occurring at that time instant. Okay. And so this gives us the scaled Dirac deltas. So these are the scaled Dirac deltas, Dirac delta functions. Okay. And we know that the reconstructed signal XR of t is equal to XS of t convolved with HR of t. Okay. So this is nothing but XS of t is summation n equal to minus infinity to infinity x of n times delta function, delta of t minus NTS. So this is one signal. We have to convolve. So let me put a bracket around this. This represents XS of t, and we have to convolve this with HR of t, where HR of t is given by, let's one more step, let us write it as HR of t here, HR of t. Okay. So what is happening, what happens when you convolve HR of t with a delta function? The HR of t will move to where the delta function is, and that is what you saw in the reconstruction figure. Wherever there was a delta function, you will see that one copy of HR of t comes there. And then you add all of these together with the appropriate scale factors for the Dirac deltas. That will give you the complete expression for all values of t. Okay. So, but how can we write this in a mathematical form? We can write this as summation n equal to minus infinity to infinity x of n, that is a scale factor. HR convolved with the delta function will mean that the HR now gets shifted to where the delta function is, HR of t minus NTS. Okay, so this is the reconstructed signal, very important. So wherever there was a delta function, the impulse response now shifts to that place, and then you scale it and then add it together. So basically this expression that we have here, this equation corresponds to the process that we have done, exactly what we have done. Okay, let us just take one more step and write down the full expression. So we know that HR of t is given by sine pi t over Ts divided by pi t over Ts. Okay, and we are also given the expression that XR of t is equal to summation n equal to minus infinity to infinity x of n HR, the impulse response of the reconstruction filter, being shifted to wherever the delta functions were located. Okay. Now, if you combine equations 1 and 2, combining 1 and 2, we get the expression for XR of t, which is given by summation n equal to minus infinity to infinity x of n scale factor sine pi t minus NTS divided by Ts divided by pi of t minus NTS divided by Ts. Okay. How did we get this? Wherever there is t, you substitute t minus NTS, that is all. Okay, so not a difficult expression to derive or to understand, but useful for us to explain. So basically, in equation 1, you substitute wherever t is there, you substitute with T minus NTS, right? That's exactly what is happening. So that's how we get this expression. So when you see an expression like this saying that the reconstructed signal is obtained from the samples of the discrete time sequence using this formula, you know exactly how this expression has been obtained. Okay, this looks like a complicated expression, but actually it is not, because what is it? It is a convolution of x of n with hr of t, and basically because of the delta functions, these impulse responses have been shifted. So what you see is this is a scale factor. This is a scale factor, and these are shifted impulse response functions. Okay, shifted versions of hr of t. Okay. So I am now very confident that that you have the ability to understand and to understand how the reconstruction process is working, and how we can go from the continuous time to the discrete time through an intermediate step where there are Dirac delta functions. And then when you go from the discrete time back to the continuous time, again we generate the Dirac delta functions and then convolve it with the reconstruction filter, and then what the reconstruction filter is, we can understand by looking at the Fourier spectrum of the sampled signal. So please do look at this material more carefully, go through it, understand what the concepts are, and definitely you will find that this is a subject that is, this is a topic that will be of interest and will be something that you will be able to understand and apply very nicely.